All right, so let's review for today's quiz, which is the material from last week, and it was on what, loops?
Yeah.
Yeah. So this will be quiz 3. Let's look at the. Let's pick some problems from the list here. Tell me which problem you'd like to look at. And there's answers in there, but I'll talk about the answers. I decided to put the answers and everything. I did that over the last couple of days. Which problem do you want to look at? The code reading problem or a code writing problem? A writing problem? 7, 8, or 9? 9. Guess the number. That's it up here. Where's guess the number? Is it up here? Oh, it's in the. Oh, here it is. So we have to guess a number, and so we decide on a number that the user needs to guess, and they type in a number, and they say, we say, well, it's too big or it's too small, and we let the user perform binary search, right? So it'll look like enter a number. What number is it?
1776.
Huh? 1776, yeah. So let's do an infinite loop. And let's enter in the number. Say n. Read the number. Once you read it in, we'll check it. If n is bigger than 1776, then we're going to print it's too big. Else, if just like that binary search algorithm. Now we're going to check to see if n is less than 1776. I say that's too small. And else, you see my indentation? I've got these substatements. It's an if, else statement. I'll say, you got it. Now, of course, we want to do one thing. We want to break from the loop as well. So break. So it's an infinite loop, and we're going to break out of it when the user answers the question. So we'll try this one. What's the number? 1775. That's too small. What number is it? 1776. You got it. So on. Control C to break. So it's just kind of like manual binary search, right? The human is doing the binary search. This is the future, right? In the future, we're going to be the slaves, and the computers are going to be the masters. Once the AI gets strong enough, they're going to have us do these jobs. Yeah.
What part makes it go backwards? Is what number is it to make that loop? Is it the true part?
So one more time.
What part on the code makes it repeat to where once you put the number in, it reads it out and then goes back to the start? What part of the code is it? Is that the walkthrough?
So what part makes it repeat? Well, look at the loop. The loop does the statement, what happens inside the body of the loop. So the body of the loop will repeat over and over again. Let's see what happens. We say what number is it? Then we declare an n. We read the n. And then this is one statement. That's just one statement. And then we test. And we get the substatements. So there's 4 statements in the loop, and they repeat forever. So after, let's suppose that in this if-else-if statement here, we've got 3 sections. This one, and this one. Only one of those 3 sections will execute. Now, if this section executes, what do? We print. And then after we print, we repeat the body of the loop because the loop condition is always true. So if we execute this group of substatements, well, it's one substatement, then we finish we don't do anything else. You know, if this condition is true, execution goes into these substatements, runs it, and execution does not even come into here. It doesn't even bother. After this is determined to be true, we run line 13 immediately, and we don't even look at this. We don't even go in there because it's else. Well, I don't need to else. I already got it for true. See, so that's why the loop will just continue until we hit this block. This is where the n is neither greater than nor less than 1776. So we say you got it, and then we also break. Break means exit the loop that I'm inside of. Is that good? Is that all right? Okay.
If you, instead of doing an infinite loop, could you do while n is not equal to 1776?
Yeah.
And then would you not need that break statement?
Yeah, that's a good idea. Let's do that. We don't need the break statement now. The only thing is, this code will not compile.
Yeah, you need to initiate n outside the.
Yeah, we got to put n out. Oops, sorry. We got to move the declaration of n outside of the loop. Now, n is kind of a random value here, so let's assign it something, right? I don't know, like, we know it's a 0 is not the number we're looking for. I mean, it's possible that memory could accidentally have a 1776 in it. It's quite unlikely, but it might happen. So this will work. Let's try that. Another thing we could do here is, well, when n is that number, we exit the loop. So we could put this out here as well and get rid of this clause altogether. You know, if it's greater, then we say it's too big. If it's less than 1776, we say it's too small. And then we just continue with the loop condition. And as soon as the loop condition is false, we finish this. It must be the case that the user entered the number correctly. So then we can print this outside the loop. So there's several variations that you can experiment with. Whatever is the most readable, because they're all equivalent in terms of efficiency. Which one is the most readable? That's what the decision comes down to. Anything else? More on looping. So we have this, how about prime? This one is important. I hope you all know, and factoring. Do you want to look at either of those?
Yeah.
How many people got factoring done? Oh, that's great. That's fantastic. Do you want me to do prime or factoring? Which one do you want me to do? How many people want to see prime next? How many people want to see factoring next? So factoring, okay. So we want to ask the user for a number. So maybe the user enters 100. The program displays the prime factors. So if the user enters 100, we'll display 2255 because 2 times 2 is 4, times 5 is 20, times 5 is 100. If the user enters in 23, the program prints 23 because there's only one prime factor. It's itself. It's a prime number. So let's get this to work. So we'll enter a number. And then we're going to, we'll have a loop. And inside the loop, we'll print the, we'll generate these factors. So what we do is we start at the small numbers and try to take out 2s. We'll take out as many 2s as we can, and then when we're done, we'll try to take out as many 3s as we can. And then we'll try to take out as many 4s as we can. We won't be able to find any 4s at all because we've already taken out all the 2s, because 4 is 2 times 2. But I don't want to have to skip 4 because then I have to do a prime test. So you can do that. You can say, oh, is 4 not, you can have an is prime function and test to see if 4 is prime. If it's prime, we'll skip 4. And that's how I used to solve this problem, but then I realized that, well, let's just test the 4 directly and don't have to use the is prime test on it. It's actually faster. So what we want to know is we've got some kind of a divisor, say I, start at 2. And if the number n is evenly divisible by I, we know that we've found a factor. I is a factor. So we're going to print I. We're going to print I. And then we're going to take I out of n. So you have to reduce n by I. So if it's 100, right, if n is 100, if the user enters 100 for n, and we initialize I to 2, then 100 mod I, 100 mod 2 is 0. Whoops, I made a mistake there. I should be 0. if n mod I is 0, if 100 mod 2 is 0, which it is, then we'll print the 2, and then we'll reduce 100 by 2. So we'll take 100 divided by 2 to get 50, and that's what we have left. And then we'll try to keep taking out another 2. We'll be able to take out another 2 at this point. And we'll print another 2, and then we'll reduce n from 50 to 25. When we're at 25, we won't be able to take out any more 2's. So this test will fail. And when it does fail, we want to go to the next number. So we increment I. We're going to try 3. So if we have 100, we took out 2 2's, so now n is now 25. 3 doesn't go into 25, so we're going to increment I to 4. 4 doesn't go into 25. Then increment I to 5. 5 goes into 25 5 times, so we're going to print the 5, and then we're going to take a 5 out, leaving 5 remaining. Goes to the loop again. 5 is divisible by 5. 5 mod 5 is 0. We're going to print out the second 5. And I'm going to remove the second 5. So 5 divided by 5 is 1. So now n is 1. N becomes 1. We don't want to go any farther, right? Once n hits 1, we're done. So there's the loop condition. Well, n is greater than 1. Do the loop. And just for neatness sake, let's print out a new line at the end here. Oops, n was not declared in this scope. There we go. You know what? I'm going to kill it right there because I didn't like that space. Just going to fix that. N is 100. 2255. That's great. 27. 333. Look at that one. That's interesting. And that was pretty fast. Any questions on this one? All right. How about prime numbers? Do you want to look at that or not? We could just call it quits at this point, or look at something else. What do you want to do? Is that it for today, or do you want to look at another one?
To look at the prime numbers.
Prime numbers?
Yeah.
Okay. This one, you really got to know this by heart, you know, how to print out prime numbers. So maybe the user enters in a prime number, okay? The user enters in a number, rather. And we want to say whether it's prime or not. We're going to say it's not prime. This is a stub, right? Oops, Endel. Not prime. So, well, 23 is prime, so that we have to get the logic in there now. So we'll have a loop. Basically, what we want to do is try to divide n by all the numbers less than n. If we find a divisor, then it's not prime. But if we can run through all the numbers and not find a divisor, then n is prime. So inside the loop is where we declare that n is not prime, because in the loop, that's where we find a divisor, and it's outside the loop that we can declare that n is prime. It's outside the loop that we know that we finished the loop, that we did not find a divisor. That's the point where we can declare primeness. It's in the loop when we find an individual case that we found something to divide into n. At that point, we can declare it's not prime. So we're going to try all the values starting at 2. Everything less than n. If n mod I is 0, that means we found it. Found a divisor. We print not prime. Then we have to get out of the loop. We don't want to keep checking, right? So we can return from main, actually. Because main returns an int there, so you have to return an int, so 0. So we don't want to hit, we basically don't want to hit this statement here. So we're returning inside the loop. If we break from the loop, then we're going to have to use some extra coding to skip this, this line. Actually, I just remembered a solution that a student did, I think last quarter. I'll show you that solution. 23 is prime, 100 is not prime, and so on. There we go. Another way to do this is a solution a student gave already. Here, I'll show this to you. What they did was that that person broke here, and they had this, they had an else statement here. Else if I is n minus 1, this is their solution. So they didn't want to return from the function. If you find a divisor, then you print not prime and you break. And if we're at the very last n, right before the end of the loop, because if I is n minus 1, that means when we increment I will be n, and the loop condition will fail, and we'll exit the loop. So if we're right at the very last iteration of the loop, this condition is true. This means we're at the last iteration of the loop. So if we're at the last iteration of the loop, and this condition is false, then we know it has to be prime. So this is how they did it. So it works. I mean, you know. So it's good. But it might be cleaner just to have a function here. Just take a number, say n, I'll call it n not k. Well, that doesn't matter. We're going to return true or false. If the Boolean value is n prime, return true. If n is not prime, return false. So this code needs to get moved up into there. So now what we do is we have this statement here. If is prime n, else, right? So if is prime is false, we want to print not prime. If is prime returns true, see now the function returns true or false, so we're using it as a condition in the if statement. If is prime returns true, we're going to print prime. We don't want to do printing in the function. See, it's not good style, because it's creating a confusion about the responsibility of the function. A function should have a narrowly defined, clear responsibility. The function just returns true if n is prime. We don't want to do any printing inside the function, because we don't know how we're going to use the function. I mean, we do in this problem, but later we might want to use this function for some other purpose that doesn't involve printing anything. So we just want the function just to return true or false. The printing, for the user's benefit, that's done in the code that calls is prime. Yeah.
Would you still want break in the function?
We got to fix this, yeah. Let's fix this. So here, we return false is not prime, else return true it is prime. Sorry. So there's the function. So if we get an n, is n prime? Let's try to divide n by 2, then by 3, by 4, and so on. If we find an I that divides into n isn't prime. So we got to return false. Now if we finish the loop, and we go to line 10, it means that we never returned, right? Because return would exit the function. We never get to the last line in line 10. So we finish the loop, and means we didn't return. Then we're going to return true because we tried every possible divisor. I want to tell you that it's a little more efficient if we use the square root of n here, because something bigger than the square root of n is not going to evenly divide into n, right? So but you don't need to remember that. For the exam, you can omit that detail, but that does make the code run faster for larger numbers. Square root is not defined. Any suggestions?
Include the C.
Yeah, good, thanks. So it's pretty much the same thing. There we go. This is where we're using functions to organize our code. There's the function. I want to mention one thing about functions. I think I talked about this before, we can move this down here. If this is a better organization for you, that we can do it like this, but this will fail to compile because is prime is not declared at this point. So what we can do is use what's called a forward declaration. I think I covered this already, but I just want to repeat it. See, I'm not implementing, I just put a semicolon there without braces. We're not providing an implementation of the function. We're just saying the function exists. It takes an n, an integer, returns a bool. The name of the function is prime. I'll get around to telling you what the implementation is later on, but you can assume, compiler, that is prime will be defined at some point. So go ahead and make that assumption. So when the compiler gets to this line, it says, well, oh, is prime doesn't yet exist, but I've been given a promise up in line 7 that it will exist. And so that's called a forward declaration. Oops, I have to compile it. Now we could break our promise. All right, and not do it. It doesn't say, you know, is prime identifier undeclared. It doesn't say that, right? It says it's a different error message. This is called a linkage error. It actually did a compilation, but it went to link. It means it looked at these references to functions and it tried to wire them up so that, you know, those places in the code that call a function, we have to now connect it to that function, but it couldn't find that. So that's a linker error. So in a Unix system, the linker is normally LD. It's called LD, that's the name of the command. See, if this was omitted, now it won't be a linker error anymore because we've gotten rid of the forward declaration. Now it'll be an undefined reference. Is prime was not declared in this scope. It's a different error now. See the difference between a compilation error and a linkage error? This generates a compilation error. Like we can tell it just to compile. I'm going to go -C. It means don't link, just compile. No error. See, no error. Now, it doesn't generate an executable. It generates main.o. See, and that's called object code. That's a intermediate file that is now passed to the linker, and the linker will try to resolve the references to functions. But it won't find as prime anymore, so we'll get a linkage error. So we won't be able to generate an executable. That's it. Any last questions? Yeah.
Is there any point in time that we would implement the function after the main, or is that just something?
Yeah, no, it has to do with your style, how you decide to organize your code. Definitely, this happens a lot. Yeah, for sure. It could be that's, you know, you might be in a like working in a team that has lots of code, and main is always at the top in all the programs. So let's not do it any differently because that reduces readability. Let's keep the style the same. So whenever we generate a new program, let's put main at the top like we've always done here. So that's an example where you would want to do that. All right, that's it.